Hi everyone, I'm going to explain mathematical induction, what it is, how it works, and show you one clear example to understand this important proof technique. Before we jump into the example, let's quickly review the idea of induction. Mathematical induction is like a chain of dominoes. If we knock the first one down and show that each one knocks the next one over, all of them will eventually fall. That's exactly what we do here. First, we check the base case to make sure the formula works for the smallest number. Second, we assume that the formula holds for some number of k. Finally, we use the assumption to show it also holds for k plus 1. If we can do all this, then the statement is true for all natural numbers. Okay, let's begin with the base case when n equal to 1. On the left hand side, we have 4 times 1 minus 1, which equals 3. On the right hand side, we have 1 times the quantity 2 times 1 plus 1, which is 1 times 3, which also equals 3. Both sides match perfectly, so the base case is true. Okay, next we assume the formula is true for some arbitrary number k. That means we assume that the sum up to the k term is k times the quantity 2k plus 1. This is called the inductive hypothesis, and we will use this assumption to help us prove the next step. To go from k terms to k plus 1 terms, we need to add the next odd-looking numbers. That's 4 times the quantity k plus 1 minus 1. So starting from the left-hand side, for k, we add 4 times the quantity k plus 1 minus 1 and simplify. This will help us see if we can obtain the formula for k plus 1. Okay, now let's simplify carefully. Start by expanding the expression k times the quantity 2k plus 1. That gives 2k squared plus k. Now we add 4k plus 3. Combine the like terms to get 2k squared plus 5k plus 3. Now we try to factor this trinomial. We find that it factors nicely into the quantity k plus 1 times the quantity 2 times k plus 1 plus 1. This shows that the formula holds for k plus 1, completing the inductive steps. So, for conclusion, by verifying the base case and proving the inductive step, we have completed the mathematical induction process. That means our original sum formula is true for every positive integer n. Mathematical induction is a very powerful tool. You can use this same method to prove other statements that depends on n as well. Finally, this is the link of reference of the topic mathematical induction video. So, if you like to see more example or need a refresher on the topic, you can watch this video. That's the end of my presentation. Thank you.
Next, my name is Isabita Aziz. I will presenting the topic 2 function for this group assignment. This presentation will cover the definition of function, types of function, invertible function, compositing function, and some examples to support our understanding. So, let's start. First and foremost, what is a function? A function is a special type of relation from set A called the domain to a set B called codomain, such that every element in A is assigned exactly one element in B. In other words, for each input, there is only one output. For example here, if we define function s equal to 2s plus 1 and the domain given is 1, 2, 3, then we can compute the f1, f2, and 3 by substitute this value into the function s. So we get the 2, 5, and 10 respectively. So this satisfies the condition of a function because each input maps to only one output. Next is a special types of function. There are 3 special types of function we need to understand. First is one-to-one, or we call it as injective. Each element in the domain maps to a unique and different element in codomain, and no two inputs have the same output. The second one is onto, or surjective. Every element in the codomain is used. That means for every output in set B, there is at least one input from set A. The third one is bijective. A function is bijective when it is both one-to-one and onto. This means there's a perfect one-to-one matching between domain and codomain. Here is a visual representation of injective, surjective, and bijective function. On the left, you see each input going to a unique output, so we call it as an injective. And in the middle, every codomain value is used, so this is a surjective. And the last one is on the right, both properties are satisfied, and this is bijective. So all of these diagrams help us quickly to understand the structure of a function. Next, let's identify types of function. Let's say we have a function defined by fs equal to 2s. To prove that it is injective, we assume if fs1 equal to fs2, then 2s1 equal to 2s2, and final result we get s1 equal to s2. Since the result shows the input must be equal, the function is injective. If the function covers the whole codomain without any missing output, it is called surjective. Therefore, if both conditions are met, the function is bijective. Next is invertible function. A function is invertible if and only if it is bijective. The inverse function written as f inverse s undoes the effect of the original function. For example, let function x equal to 2x plus 3. To find its inverse, first we need to set y equal to 2x plus 3 and then solve for the s. And we get the s equal to y minus 3 over 2. And therefore, the function inverse s equal to s minus 3 over 2. If we apply f inverse to the output of the fs, we get back the original input. That means f inverse s equal to s and f inverse fs equal to s. So, you get the same output. Now, let's move on to function composition. Function composition means applying one function to the result of another function. It is written as f of gs equal to f gx, or we can read it as f composed with g of s, or simply apply g first then f. The function that closest to the input s is applied first. So here we can see the example. Let fs equal to s and gs equal to s plus 1. Then first let's solve for f of g function. F of g function equal to fgs and equal to fs plus 1. Now we can plug 2s into the function f. We get fs plus 1 equal to 2s plus 1. And we can simplify the 2s plus 1. We get 2s plus 2. Next, let's find the g of f function. G of f equal to gfs, and you get the g to s. Now we can plug the s plus 1 into the function g. We get g to s equal to 2s plus 1. We should take a note that f of g not equal to g of f. So, composition is not a commutative. I have included a video link that explains function in simple and visual way. It shows how inputs are mapped to outputs and make concepts like injective and composite function easier to understand. So here, I very recommend to watching it after this presentation to strengthen your understanding of this topic. Alright, that's all for me. Thank you.
Hi everyone, I'm Karina. Today I will be presenting about the pigeonhole principle, which is one of the interesting topic in discrete structure. This principle may sound simple, but it is very powerful in solving logic and counting problems. The pigeonhole principle is a simple idea. It says that if we put more items than containers, then at least one container must hold more than one item. For example, if we have 13 socks but only 12 drawers, then one drawer must have at least 2 socks. This is basic idea of how the pigeonhole principle works. Now let's look at the basic pigeonhole principle. If we put n items into m containers, and if the number of items is more than the number of containers, then at least one container will have more than one item. For example, if we have 5 pigeons and only 4 pigeonholes, then one pigeonhole must have at least 2 pigeons. This helps us to understand how grouping works in real life too. There is also a more general form of this principle. It tells us exactly how many items must be in at least one container. If we put n items into m containers, then at least one container has at least n divided by m and round up items. For example, if we have 100 people and only 12 months in a year, we do 100 divided by 12, which is 8.3. When we round it up, we get 9. So at least 1 month will have 9 or more people born in it. So let me share my own example using fruit and baskets. Imagine we have 15 apples and we want to put them into 4 baskets. Now we use the pigeonhole principle to see what will happen. We divide 15 by 4, that gives us 3.75. When we round it up, we get 4. So at least one basket must contain 4 or more apples. It's impossible to place 15 apples into 4 baskets without having one basket with at least 4 apples. To help you understand the pigeonhole principle better, I included this video from YouTube. The video is made by Spanning Tree and it explains both the basic and generalized pigeonhole principle using clear examples.
Hello and welcome everyone. My name is Nur Rabiata Dawia binti Syabuddin and my number matric is 298438. Today I will be presenting topic finite state machine, also known as FSM. This topic is very useful in computer science and system design to describe how a system change based on input. Let's explore what it means and how it works using a simple real world example. Now I will explain what is finite state machine. Finite state machine is a model used to describe the behavior of a system that change between a limited number of states based on input. FSM is made up of five main components. First is a finite number of states, for example S0, S1 and S2, a finite set of input, for example 0 and 1, a transition function that determine how the FSM move from one state to another, and a start state, and the last one is one or more except or final state, where the system may stop. Next, in this slide show a basic transition table and state diagram. The transition table tells us which next state the machine will go to depending on the current state and the input. The state diagram is a visual version. Each circle represents a state and the arrow represents transition, with labels showing the input needed for the change. For example, from state S0, if input is 1, we move to S1. If the input is 0, we stay in S0. It followed by another state until the end. Now let's apply finite state machine to a real world case study, which is a vending machine. Imagine a vending machine that sells drink for 3 ringgit. The machine only accepts 1 ringgit coins. So we will model the behavior of the vending machine using an finite state machine. The input are 1 for a valid 1 ringgit coin, 0 for an invalid coin or no coin. Once 3 ringgit is collected, the machine dispenses a drink. In this slide, we can see that this vending machine has four states. S0 represent 0 ringgit inserted or starting point. S1 represent 1 ringgit inserted. S2 represent 2 ringgit inserted. S3 represent 3 ringgit inserted. And now the machine will dispense the drink. If the user enter an invalid coin, input 0, the machine reset to S0. The machine continues to transition to the next state until 3 ringgit is collected. Here is the transition table for the vending machine. It shows what happened in each state when the user enter either a valid coin represented by 1 or invalid coin represented by 0. We have four current states represented by S0, S1, S2, and S3. We have two input. input equal to 0 and input equal to 1. In input equal to 0, we have S0 for current state S0, S0 for current state S1, S0 for current state S2, and S3 for current state S3. For input equal to 1, we have S1, the current state is S0, S2, the current state is S1, S3, the current state is S2, S3 is the current state is S3. As you can see, if an invalid coin is inserted at any time, we go back to S0. When we reach S3, the machine dispense the drink and remain in that state. This is the state diagram of the vending machine. It clearly shows the false state and how the transition happened based on input. S0 move to S1, S1 move to S2, S2 move to S3 using input 1. From any state, if input is 0, we return to S0. Once in S3, the machine stays there until reset. This diagram is an easy way to understand how the system works step by step. For the reference, I use this video as part of my reference to understand the finite state machine and how to apply it. It helped me visualize how finite state machine is used in real life, especially in simple systems like vending machine. And I think that's all from me. Thank you for listening to my presentation.